ايه
اتفضلي يا
اكتر
بيه.
حاجة حسيتها انها نفعتك في انك تتقبل في الجينيتك او تشتغل في الجينيتك؟
النصيب يا بنتي والله. اه والله ما
اكيد.
بقى يعني أم يعني هو الواحد بيسعى وبيحاول يعني يعمل اللي عليه، بس هو في الآخر النصيب يعني. بس هي دي الإجابة الحقيقية. عايزة بقى نتكلم عن الأسباب، ناخد الأسباب ل... يعني ناخد الأسباب نتكلم عنها، بس مش هي دي السبب. يعني هي اسمها الأسباب بس مش هي السبب. أه... بس ده كلام يعني، ده موضوع يطول الكلام فيه. ممكن نبقى في الآخر كده، في آخر الكورس نبقى نعمل مرة كده ندردش فيها مع بعض عن يعني career planning career choices. اللي عنده أي أسئلة general يسأل عنها. بس هو موضوع يطول فيه الكلام يعني. طيب أوكي. حاول.
النصيب يا بنت. نصيب.
أنا عملت شير سكرين. حد يقول لي إذا كان التكست يعني legible كويس. عارفين شوف أنا مش شايف مش
Can
شايف
you
انتوا
please
شايفين
zoom
ايه.
in?
I can zoom in more.
Yes, please.
How about now?
It's clear, thank you.
Okay. طيب let's start إن شاء الله. Um, the last few sessions, alhamdulillah, we finished introducing the different aspects of training a neural network. يعني الأول we talked about إيه هي neural network, what exactly do we mean by training the neural network, and we talked about the flow of data, the forward propagation. We talked about the math, what exactly happens, how does the data move from one node to the next until the output layer. And then the last time we talked about how we train the network parameters, the weights and the biases. We talked about backpropagation, and hopefully you have taken some time to digest some of the concepts. Um, فالنهاردة today إن شاء الله uh, we're gonna go to Python and start looking at the implementation of these concepts. Um, you'll see how libraries like PyTorch abstracts away a lot of the details that we've talked about. Like you will see that with only a few lines of code, you could define a network, feed it some data, have it train, and then give you an output. So we have a couple of examples today. One example with a regression problem, just a very simple problem, and another example with a classification problem. If you recall from the first lecture or the first class, um, we defined the problems within the machine learning into, two big categories. And we said a regression problem means that we'd like to predict some continuous value. So for instance, if we have the example we gave then is if we have, for example, some parameters of a house, some features of a house, can we predict the price? And obviously the price is a continuous value. It could be any number. Um, and then the other major category was the classification problems, which basically entail that you have a few categories and you would like to classify a data point into one of these categories. An example would be a picture the picture of an animal that can belong to one of many categories, a cat, a dog, a horse, a sheep, and then the goal of the model is to look at the picture, you feed it a picture, and it returns a proper classification of that picture. But you can imagine that this could also be, for instance, in the biology, this could also be a gene expression profile that classifies a cell by its type. So you give it, for example, the output from a single cell RNA sequencing experiment, and you would like to know, given the expression data or the count data from the sequencing, can we classify this into its proper cell type, its correct cell type? Um, so because this is the first time we introduce some of these concepts, I'm gonna take my time and explain some of the stuff um, about how the package works and how some methods attached to it that are more commonly used. But I mean, obviously, we cannot really cover bases. We cannot cover all the bases of like something like PyTorch because it's a massive library. There's a lot of things that we haven't discussed yet theoretically. And we're going to introduce a couple of new things as well as we work today. Um, and it's always nice to build a habit of checking the documentation as you go. Like for instance, if you're not familiar with what the methods attached to a certain class is, you can always go and read the documentation from that package. And maybe there's something that you would like to use that you weren't aware is there. So it's nice to check the documentation every now and then. And I mean, today, with the existence of ChatGPT and the likes of it, a lot of us, myself included, have gotten a lot lazier when it comes to documentation because it's always easier to ask ChatGPT about something that you'd like to do and then hoping that they're going to give you the right class to do it. But I mean, if you'd like to build a good habit, check the documentation. That's the right thing to do, I guess, for now. All right, so I have sent the link. I pushed this into a repository on GitHub, and I've sent the link to the notebook if you'd like to follow along. If you haven't set up an environment and you're not really familiar with how this works, I would not try to play with it for the time being and just focus on the like how we like focus on what we discuss right now, and then maybe afterwards you have access to the notebook, and then you can take your time afterwards and try and run it yourself. In order for things to be simple, I just included the packages that we're gonna need here. So you just have to create a new environment. I use Python 3.11, but like this is what I tested. So maybe use the same version just to make sure you don't run into any dependency issues. And I usually use Conda to start new environments. But there's other ways you can start virtual environments. So whatever you're used to, feel free to use it. So this cell here is just to install libraries in case you don't have them. And now after installing them, we are importing them. And then this cell here, we're creating some synthetic data. So the first problem we're going to deal with is a regression problem. So we are trying to create some fake data that are basically X and Y's. And to make sure that there's some trend linking to them, Y is basically just a function of X. This line, I'm specifying that I would like 30 data point rand and creates basically random numbers from a normal distribution with the dimensions that I give it. So I'm giving it the n, which is the 30 I specified here, and times 1. So this basically creates a matrix of 30 times 1. Random numbers, as we specified, sampled from a normal distribution. And then y is our y variable, obviously, which basically takes x and adds some noise to it. The noise is, again, just some random numbers divided by 2. And I mean, you can obviously change this and change how much noise you add to it and whatnot. But you can play around with it. And this is just to plot the data, see what kind of data we get. So it's actually, this is too much code just because I like to have my color scheme be consistent between the plots. And this is probably similar to what you see on the slides. So most of this code is actually just to make it look like this. And because I use a dark background, it looks like this. If you use a white background, it might look a little weird. But yeah, anyways. So like this is the data we created. You see, these are the x values, these are the y values. And because these are random numbers, if I run this cell again, like if I come here and run this again and I visualize it, it's going to look a little different. I'm hoping you see the difference now that this looks slightly different than what we did before. So like I can run it again, and every time I run it, you see that it gives us a different looking distribution because it's basically random. Okay. So let's run again. All right. And now we build our model. So remember everything we talked about in terms of like in the nodes and the inputs and stuff. This is basically how, in these 4 lines, this is how you build a model in PyTorch. It's both like nice and sad at the same time, because you learn so many details about how stuff works, but at the same time, which is like it feels a little bit unnecessary if it's so simple to create the network, but it's also nice to understand what is happening under the hood. So there's actually different ways of building the models, but because this is the first time, the easiest way is to use this sequential class. So, okay, so we're using a module in PyTorch called NN. So if you go to the imports here, we are importing torch.nn as NN. NN is short for neural networks, I suppose. And this is a module that comes from PyTorch. And within the module, you have this sequential class, which allows you to essentially stitch up different components into a neural network, basically. And remember, with neural networks, we talked about an input layer. This is where you feed the raw input. There's not really any computation happening besides just supplying the raw inputs. And then these are connected to the first, if you have many hidden layers, but in this case, we only have a hidden layer. And we said within the hidden layer, there's 2 kinds of computations that happen. There's the linear combination of the different inputs, which is basically every input multiplied by the weight attached to it. And then you add a Bayes term. And then this is called the pre-activation, which then passes into the activation function, which is the nonlinear function. And we talked about different kinds of nonlinear functions. And then the output of the hidden layer gets passed to either the next hidden layer, or if this is the last hidden layer, it gets passed to the output layer. And within the output layer, the same math applies. So the output layer is basically a linear combination or a weighted sum of all the nodes in the last hidden layer plus a Bayes term. And sometimes some of these some of these output layers can also have their own activation functions. If you recall, we said usually when we are dealing with regression problems, because we're interested in the continuous range of numbers, we tend to not really transform the output. But if we're dealing with a classification problem, for example, then we can use an activation function to transform the output numbers into probabilities. Can someone remind me what activation function we mentioned that
Sigmoid.
yields? Sorry?
Sigmoid.
Okay, sigmoid and
soft max.
what's the difference?
Sigmoid is used in binary classification or softmax is used in multi-class classification.
انا منبهر يا جماعة، انا منبهر. لا مش ده، سوري. كان في صوت تسقيف، سمعتوه ولا
ما
مش
سمعناهوش بس
شغال؟
وصل.
نعم.
هو ما سمعناهوش بس وصل.
اه طيب تمام. معرفش مش شغال ليه. لا استنى بس، دي حاجة مهمة دي. استنى كده، جرب كده. وصل كده ولا لا؟
لا برضه، بس برضه كأنه وصل.
معلش طيب، المرة الجاية اظبطه ان شاء الله. طيب مظبوط. sigmoid function is sigmoid function and softmax functions are both used in the output layer. The difference is sigmoid function is used when we would like to do a binary classification, meaning we only have two categories. And when we have a multi-class classification, this is when we use the softmax function. Okay, so that was just a quick recap. So let's see how this is done here. So in PyTorch, you have with the sequential class, you define uh, a linear layer, I guess, using this nn.linear, and then you give it the dimensions. So these dimensions are essentially the easiest way to think about them is the first argument becomes or is or accepts the input of this layer, and the second argument defines the output of the layer. So in that case, we're telling the network or we're building the network such that it receives a single input or a single data point, and outputs or passes to the next layer also a single output. And then after this only does, like this line here, only does the linear combination of the data coming from the previous layer. And then if we would like to use an activation layer, we define the activation layer into a separate call, which is an n.relu. And then you can imagine that within that module, there's also other activation functions that we can use. And this is, again, the like if you haven't done this before, this is the utility of opening the PyTorch documentations and looking at the NN module, seeing what are all the options that are predefined there, and if there are no, if you would like to use an activation function that is not predefined, you can easily just code this using a math. Like you can define this as a mathematical equation because at the end of the day, all of these functions are just mathematical equations. And if you go to your slides, with every function that we defined, I put in the actual mathematical formula for the function. So you can easily just, if there's an activation function, for example, that is never used or is not predefined in PyTorch, you can customize, you can build your own and put it within the layer, within the network. And then the output of this, so these two lines are essentially just defining the hidden layer. We're just splitting this into a linear component and a non-linear component. And then what comes out of this goes into the output layer, which in that case is just, again, the linear layer has to be there all the time. Like every time you define a layer, because that's usually the first step. So you do the linear combination of all the inputs coming from the previous layer, and then if you have an activation function, then you would define it afterwards. But again, because this is a regression problem, we just leave it at that, and we take the linear combination from the output layer, and this would be our predicted y value. Okay? Any questions? Hopefully this is simple enough. But if anyone is confused, please feel free to ask questions. Okay. So what I've put here for you, because these are things we're gonna see in like some of them today and some of them in future classes. These are common methods that you could call from the NN module. And one of them, for example, is the dot train. This puts the model in the training mode, and the dot eval, this puts the model in evaluation mode. We haven't really talked about training and evaluation yet. Um, but the idea is, I'll just give you a small introduction, maybe. The idea is sometimes we would like some of the nodes to be handled differently. For example, if anyone recalls, we talked about something called dropouts, which is the process where we intentionally tell the model to ignore some of the nodes during training. But this only happens during training, meaning that if the model is training, we can choose to switch off some of these nodes. But as we evaluate the model, as we evaluate how well the predictions are working on a test data set, so after the training is done, we have to turn on everything, meaning that the dropouts only happen as we train the model. And when we go and evaluate the model or test the performance of the model on real data, we turn on everything. This like these functions, these easy functions here allow us to control which state the model is in. If we're training the model, if the model is in the training mode, then we can apply the dropouts and like the model knows that it's training. And now after it's trained, we want to tell the model, now you're being evaluated. Don't drop out anything. Don't apply regularization. Um, this is our way of telling the model in what state it is. We're not going to use this today, but this is going to be handy in the future. This is also another thing. We're not going to use it today, but this is very useful. The dot requires grad. This is basically we're turning on or off the gradient tracking. So this is something really nice about PyTorch. It makes tracking the gradients really easy throughout training. Remember last time when we talked about gradients and backpropagation and everything, as the model moves through or goes through training, there's usually like gradients that it builds so that it decides which direction it moves towards minimizing the loss, right? And PyTorch does a really nice job that it keeps tracking these gradients so that when you want to expose them at any point or see what the gradients are, or use optimizers that would change their behavior based off of this gradient, you can turn this on and off. And sometimes you would like to do something called the weight freezing, meaning that, for instance, in models, in big models like the large language models, if you've heard this term before of pre-training and fine-tuning, sometimes this basically implies that you get like one of those large language models that are just pre-trained by Google or OpenAI or one of these companies. And you would like to use this model, but you would like to refine its performance on, let's say, some biological data or some chemical structure data or what have you. So in a sense, you would like to improve this model, but you don't want to mess up the model performance too much. So one thing you could do is you could freeze the weights. So like you tell the model, don't change any weights, don't track any gradients. I would like to use it as it is. But then you maybe add a layer or two at the end of the model that basically would be trained on like this biological data or the chemical structure data or whatever that you added on top of it. So this gives you a nice, easy way to turn on and off the gradient tracking and also to freeze the model weights. This zero grad is basically zeroing out the gradients of all parameters. And this is basically something that you use in every network you train because with every epoch you go through the data, you would like to erase the information of the previous gradients so that the model can learn gradients with every epoch from the beginning. If you don't clear out the gradients from the previous steps, the model keeps on stacking the gradients on top of each other. So it becomes very misleading to the model. So remember the last time when I showed you the stepwise gradient descent, and every time, like every step, we calculate the gradient, and then using that gradient, we multiply it by the learning rate, and then we calculate the new parameter from the old parameter. Um, like if you don't clear that gradient with every step you do, you're basically summing up these gradients by default. This is the default behavior of PyTorch. And because this would basically imply that like at every step, you're not really calculating the gradient. You're calculating the gradient of that step plus the gradient of the previous step, or steps if you're doing this many times. So this is very essential in training any network, that you, with every step, you clear the parameters before you compute the new gradient. Backward is basically the entire lecture we talked about last time. So dot backward is basically computing the gradient of the loss with respect to parameters, which is basically the back propagation. So it's called backward. So when you call dot backward, you're basically running back propagation on the entire network. And then the dot step is basically taking this is the update equation. So it's taking the old parameter, and then subtracting the learning rate times the gradient that you computed. So these steps, like we talked about extensively the last two times. This calculates the back propagation, and then this updates the gradient that you calculated times the learning rate, and then subtract this automatically from every parameter to give you the new parameters. Okay. These are the state underscore dict. It gives you a dictionary of all the model parameters. So if you have 1,000 parameters, it's gonna print every single parameter of those by its name, like a dictionary of its name and then its value. This way, if you would like to know like the value of a certain weight, for example, you can retrieve it there. Okay. And the same thing, the parameters, but this actually gives you an iterator of the parameters that you could feed directly, for example, to like the optimizer function. So when you go and call the gradient descent function, for example, you would pass in these parameters so that the gradient descent works on every one of those parameters. It knows what parameters to optimize, and this is an easy way to basically pass the parameters from your network to the gradient descent algorithm. Any questions? All right. Okay, so back to training. So this was like a little bit of a tangent. But anyways, back to training. So we built the model using a single hidden layer, which takes a single input, outputs a single output, passes this through a ReLU function, and then on to the output layer. Now, in order to train, we need to define the learning rate. Remember, learning rate, we said it's eta or alpha. Doesn't matter really how you want to call it. And then we also want to define the loss function, right? Because this is how we know whether the model is doing well or bad. We define the loss function, and the loss function is a way to compare the predicted value of the model to the real data. And from that difference, from that loss or cost, we understand whether the model is doing well or not. And then we also define an optimizer. An optimizer is basically the algorithm that we use to arrive at the minimum loss, which is what we discussed extensively last time, the gradient descent. So the gradient descent actually, or the vanilla gradient descent that we described last time, is never used in real life. There's different variations of the gradient descent that we can use because they are a little bit more efficient. So for instance, one of the very popular ones that are most usually used is called the stochastic gradient descent. The difference between gradient descent and stochastic gradient descent, and I got this text, I wrote it from you for you here, if you would like to review it. The only difference is the data that we apply gradient descent to. So the gradient descent that we described last time basically calculates the gradient for every single data point and takes the average of this and this decides which direction the training moves towards. The stochastic gradient descent does exactly the same, but for a single data point. So for example, if you have, in our case, we have 30 training examples, right? We specified here an N of 30, which means that we have 30 data points. So if we're applying the vanilla gradient descent, this would mean we calculate the gradient for every single data point of those and have a vector of 30 values. And then we take the average of these, and this becomes our gradient that we feed into the step equation, right? To update the parameters. The stochastic gradient descent, it doesn't take the average. It computes the gradient for every single value and then uses this to update the parameters. So the difference between the two algorithms is how do we use the gradient to update the parameters? Do we wait for all the training examples and then take the average and use this in the step equation, in the parameter update equation? Or do we, with every example, with every training example we feed into the network, do we take that gradient and then we update the parameters? And then, as you can imagine, using the stochastic gradient descent will become a lot noisier than the batch gradient descent or the vanilla gradient descent, because with every data point could just have a very different gradient, and you would see, like, if you're plotting the stochastic gradient descent over time, you would see that there's a lot of fluctuation and there's a lot of changing direction. When we're like, if you're plotting the trajectory, remember last time when we had like these graphs and we would just run from a starting point towards the minimum, you would see like a very smooth line going downhill until we arrive at the minimum. If you apply the stochastic gradient descent, you would see something like a lot of up and down, a lot of jumping, a lot of changes. And this is actually a little bit favorable in situations because it prevents us from getting stuck in what we call local minimum. And in order for me to demonstrate this, I just plotted this function here, which basically means that, or which shows you that if we have, hold on, if we have a loss landscape like this, and we're looking at the relationship between the parameters and the loss, if we are applying vanilla gradient descent and we start at this point over here, there's very, very tiny chances that we're gonna get out of this loss. Like if we randomly initiate the weights and to be here or here, most likely the gradient is gonna pull it this way and it will lead to us converging at this local minimum. But this is only a local minimum. This is not the global minimum of the function. The noise that you get from the stochastic gradient descent, meaning that you can bounce back and forth between here and there until you may be able to just go over this hump and land here. And if you land here, you probably will keep moving in this direction until you arrive at the global minimum. Does the stochastic gradient descent guarantee that you're going to achieve the global minimum? No. Are there more chances that you can arrive at the global minimum using the stochastic gradient descent compared to the batch gradient descent? Yes. So in other words, neither of them gives you a full guarantee that you're going to arrive at the global minimum, but you have more chances of reaching the global minimum when you use something like the stochastic gradient descent, because the added noise that comes from using the gradient from a single training example can make that gradient very jumpy and very unstable, that it can become an advantage at times. Any questions?
I have a question.
Yes.
Do we do we rely more on stochastic gradient descent when we have complex data sets? Like, is this a rule?
Glad you asked. In reality, when you have a complex data set, you usually use a middle ground. You use something called the mini batch gradient descent. So the mini batch gradient descent is basically, think about it this way. Instead of applying gradient descent to the entire data set or applying stochastic gradient descent to a single training example, you divide your training data into batches. So for instance, you have 10,000 data points. Instead of calculating the gradient for 10,000 data points, you divide it into 10 batches. And every batch becomes, let's say, 1,000 data points. And instead of calculating now a stochastic gradient for a single data point 10,000 times, you use the gradient from 1,000 points. So it's kind of like a middle ground between using batch gradient descent on the entire data versus stochastic gradient descent on a single training example. You use a middle ground in between. And this is, I think, the most commonly used setup.
Interesting. Thank you.
In real life, anyways, this becomes handy because you train in many batches anyways. Like we're not gonna deal with many batches today, or I guess in any of the models that we train in this class, because if you have to use batches, it means your training is probably gonna take longer than we would like to spend on this. But in real life, if you're training real data for models that takes days and weeks and months to train, you never train things on like the full data set. It's always broken up into batches anyways. And then you get into building like data loaders, and then you change the optimizer function and how the loss is calculated and how the parameters are updated. It's a different engineering dynamic, but everything we discussed applies. It's just now that you have to think differently about how do you handle these components given the size and the scale of the data that you have. All right. Is that clear here? Okay. So just to go over it one more time, here we're just defining the learning rate. We're defining our loss function. Again, the loss function comes predefined within the NN module. You see that we have here the MSE loss. This is the mean squared loss error. Remember, the mean squared error is usually the most commonly used loss function when we have a regression problem, which is the case now. Again, it's nice that we have this predefined, but let's say you have a custom built loss function. And actually, one of the very interesting parts of developing or creating new models is defining the loss function. How do you construct and design a loss function to really train the model to learn the things you'd like it to learn? Our problem here is pretty simple. We would like to just compare some values, some predicted values to some ground truth values. So the difference between them is easy enough for us to just use the MSE loss. In more complex problems, you will find that you can't really use a loss function off the shelf, like an MSE, or we're going to introduce something else today called cross entropy in classification problems. You will find that you actually build like custom loss functions. And again, there isn't a rule that says you have to only use the loss functions that come pre-built in PyTorch. They just did a nice job of having some of these common functions that people sometimes use for convenience. But let's say that let's say that you would like to create a custom loss function. Again, a custom loss function is simply a mathematical equation that handles your output and compares it to your ground truth in some way. And you can define this as any mathematical formula as you would like. And then you can pass it on to the training process. In here, we're also defining the optimizer, which we just talked about. So this is another module from PyTorch. It's called torch.optim, short for optimizer.sgd, which is short for stochastic gradient descent. If you'd like to know what other optimizers are available here, you can also check the documentation for this and find a list of all the optimizers that you can use. And in here, we're passing the parameters of the network that we'd like to optimize. So remember this dot parameters. Remember the dot parameters attribute that is, this is the method. The dot parameters method that is associated with this class So just not to get confused, this ANN or artificial neural network regression thing, we just defined our network to be this. So whatever this is basically just stitching the output of the sequential, the nn.sequential with our own definition of the different layers. So this is basically every method that is attached to this class would also apply to the ANN reg class. Okay. And we also, for the optimizer, we also define the learning rate because the learning rate is used to calculate or to control how much we scale our gradient, right? So last time we talked about this, we don't really take the value of the gradient as it is and just apply it to update the parameters. We usually just scale it in a way to control the step size essentially of when we update the parameters. Because we said last time if the step sizes are too big, there might be a chance that we just overshoot and cross the minimum and never really land there. Okay, let's actually run these. So here, like if you print out this ANN reg, it actually tells you that you have, this is from the sequential class, you have a linear layer which inputs or accepts an input of one feature. It outputs a single feature, and we're setting the bias to true. If you would like to train a network where you turn off the bias, all you do here is you come here and you just add bias equal false, and then it will be a bias equal false. But for now, we just like to keep the bias. And we define this, and this is just a visualization. And now this is where we actually do the training. So in training, we define the number of epochs. Remember, the epoch is every time we go around the training data a full round, this becomes an epoch. And this is our data set is really simple. So every basically think about it, if you can think about it as like a for loop. Every time you loop through the data once, this becomes an epoch. But with more complex data sets where you have many batches and whatnot, the mini batch is not an epoch in that case. The epoch is when the model has seen all the mini batches, which comprise the entire data set, only then this becomes a single epoch. Okay? Just to make the distinction between mini batch and epoch. So you decide how many epochs you want to train. It could be 10, could be 500, could be 1,000. This is a choice that you make. And also like this is just something for us to track the losses over time. So we just instantiate an empty vector of losses, which we're basically going to propagate through training. And the idea is with every epoch, you would like to basically see how the loss changes over time. So this is just, we're just instantiating an empty vector of zeros with the same number of epochs, okay? And this is how we train the model. These few lines. Essentially, what we're doing is exactly everything that we have described. So for, this is an epoch index, like where what you can call this I, you can call this whatever. So you're saying for every epoch in this range or this number of epochs that we've given you, which is 500 in that case, do these things. The first thing is to do the forward pass. So pass your input, which is X, through the network and tell me what is the Y hat or what is the predicted value. Okay, Y hat is usually something used in statistics and machine learning, that the predicted value is usually referred to as hat. And the real value is just, you call it Y, okay? So forward passes Y hat is basically the output of the network when you give it the input X. And then from this Y hat, let's compute the loss. Remember, this loss function here is basically the MSE loss function that is predefined in PyTorch. So we didn't really have to do anything about it. And if you check the inputs here, this MSE loss takes two parameters. It takes your predicted value, which is Y hat, and the actual Y value, which is the ground truth, the real value that you have in your training data. And in here, we're just recording this loss value or saving that loss value to the vector of losses that we created here. This is just for us to keep track of the losses throughout the training course. And now, so we've done the forward pass, we've computed the loss. Now we have to do the backpropagation. So before starting doing the backpropagation, remember the zero grad function that we talked about. We tell the optimizer here, which is the stochastic gradient descent, zero out the gradients. I don't want you to add this gradients to the gradients from the previous run. Make sure that these are zeroed out. And now let's compute the gradients. And then you compute the gradients using the backpropagation, which we said is called through this backward function. So this basically entails doing the partial derivative of the loss with respect to each single parameter in the network, which we extensively went through last time. This is all done in this simple line of code. And then after calculating the gradient, now use that step method to update every single parameter in the network, which basically is the old parameter minus the learning rate times the gradient, which was just calculated here. And then this is an entire cycle of data flowing, or entire epoch of the data flowing in the network, forward and then pass, and then backwards, forward and then backwards. And then with every time, like the result of every step of those basically is a new parameter, like a new weight, hopefully in the direction that minimizes this loss. Clear? Okay. Sorry, I'm just catching up with the chat. Are there any cases where vanilla gradient descent might be more favorable? I mean, if you have a really simple function, you have like a simple error landscape, you have small data points that you want to calculate the gradients all at once. Yeah. In practice, I don't recall a situation when I used vanilla gradient descent. There could be cases, maybe I can think about it and we can discuss it next time. But in practice, I don't recall using vanilla gradient descent as it is at least on bigger data sets. Why hat imposter? Yeah, imposter. Why? Well, it's not fair to it to call it imposter. It's just the model is the imposter, not the why. Okay, so this takes less than 0 seconds. Okay. And then, so in order for us to evaluate now what the final output of the model is, Noor, you're saying if the goal to find the global minima, why not calculate the second derivative? Can you tell me what I don't can you tell me what is the second derivative and second derivative of what? Noor? Second derivative of which function? Of the loss function or? Okay, I'm not sure I follow, but we can talk about this. Let's just keep going now, and then we can revisit this. Okay, so after training, basically this model now, which we defined earlier, should have the updated weights and parameters, right? So with every epoch that we've gone through here, with every step we have updated these parameters, and hopefully now after 500 epochs, these parameters are decent enough to yield an acceptable loss. So now we would like to see what the predictions look like after we pass the data through them. So we do a final pass, which is basically similar to doing like a forward pass, which is basically just feeding the X to the data into the network. And now these predictions are calculated using the updated weights that the model has learned. And then this becomes our test loss, which comes from this final set of predictions. So this again is just a way to show you that you could really just use the mean squared error and manually calculate it, which is like predictions minus y to the power of squared, and then you take the mean of it, which is what the MSE is. And then we can actually plot this. So this is basically how the loss changes over the epochs. So you see that the first few epochs, the model has actually learned quite a lot. The loss is like the decrease in loss is the steepest here. And then as you increase more epoch and as you increase the training using more epochs, it kind of tends to flatten a little bit. So if you're, for example, doing a test run here, like if we stop, for example, at let's say epoch 300, we're not really gonna lose much performance. Like the model that, like the parameters of the model at 300 epochs are not that different from the model at 500 epochs. And this is why you can kind of keep your losses in training. And in real life, you have packages like TensorFlow, for example, which lets you actually, as the model is training, lets you see these plots update in real time. So if you're training, for example, you're setting up your model to hit for like 1,000 epochs, but then as the training is going, obviously when you have bigger data, it's a much slower process. Like we trained here in like less than a second, but if every epoch takes, for example, a half hour, and you would like to do 1,000 epochs, we're talking about days of training. So for example, if you hit like 300 epochs and you're seeing that the losses are not really improving by much, you can just stop the training right there. So this is the way you monitor the losses over time is really, really important in real life.
Sorry
And then we
for
can,
uh,
sorry.
sorry for interruption, but for the elbow plot,
Mhm.
for the exact same point
An
that you
elbow.
just, sorry?
This is not an elbow plot. We're not the It's one, um, but it's not meant to behave like an elbow plot. But yeah, sorry. Go ahead. Go ahead with your question.
Yeah, yeah. I mean, yeah, it looked like an elbow, but for the first flatten, it's
Mm-hmm.
it seemed alright, but there's the second one.
Yeah.
And if, for instance, I start to see like this live, let's say, plotting
Mm-hmm.
the
Yeah.
operator, and then I
Yeah.
decide to stop at 100 because it's starting to flatten. So, is there like a way, or what's your recommendation about how to make sure that there wouldn't be a second, let's say, small elbow? Let's say,
So,
yeah.
so usually in practice, like when you think like 100 would be too early for me. Like if I see the plot is just coming down like this and I stop at 100, this is way too early. Like for example, I would like if you say like 200 for example, that would be maybe a little bit more convincing. But even then, like if I'm looking at training and I see like 200, oh, it's starting to really flatten, I would probably at least give it 50 epochs or so to run before I decide that I want to stop it there. Because as you said, sometimes the model is stuck learning something, and just it takes a few epochs, and all of a sudden it just clicks, and you see the losses dropped. Something else that this is a little bit an advanced concept. There's something called the soft start. The soft start means that you can stop the model every time, basically, when you're training those very large scale models. You create something called checkpoints, meaning that if you stop the training and you would like to start, you can start from the last phase the model was at, which is like the last checkpoint the model was at. So you don't really, let's say, I don't know, like you decided to stop at 200, and then like you talk to someone who's like, why did you stop training? You should train for longer, for example. It doesn't mean that you have to repeat the entire thing from the beginning. You can restart at 200 at that last checkpoint and continue training for a while. Okay. And there are some papers that say that when you do this called soft start, which is basically you stop the training and then you restart the training, sometimes this tends to make the loss drop a little bit better. I don't understand why this happens, and I don't think it's fully understandable in the field why it happens. It's just an empirical observation that people have reported, and this could be one way to check. Like you could just, if you feel like, okay, I'm really plateauing here, maybe you could stop the training. You can do a soft restart for like 50 epochs or something. See if the loss drops any better. If yes, you can keep training. If not, then you can just kill it and take the last checkpoint. But this is all very, very empirical, and this is all very like model specific, and this is all like there's no golden rule for you to say this is the absolute best that you can do. And actually, I would like to show you that because everything here we do is random, the data is random, the weight generation is random. I would like to show you examples where the model does really, really bad without changing anything. Like we're gonna run the same code now many times, and I will show you that the model is gonna break and is not gonna learn anything. Let's just do the one final plot. This final plot is basically just a correlation between your training data and the prediction data. So essentially, these purple points are exactly the same points that we plotted way up here. So these are exactly the same. Now, whatever the model has learned, these are the predictions that the model has learned. And obviously, you can see that the model is not really gonna learn like the model is basically as if like you're drawing a straight line between these points, and there is still gonna be differences between the real data and the prediction. But then I have a question for you here. If we have the ability to really bend and twist this line because we have some nonlinearity and we can introduce more layers, why do we stick with having basically kind of a straight line that goes through this data rather than really having a curvy line that would maybe go over these points better?
Because this would be what we call overfitting. The model will be memorizing every single point instead of understanding the pattern and being able to generalize on new points.
Okay, that's a really good answer. But can you explain why is this a bad thing? Like if we're like I mean I would really like to learn the data. That's the entire purpose of training the network. I want the network to learn the data. So
Well,
if I fit it, like if I just run it like more tightly to the training data, it means I'm doing better, right? I'm minimizing the loss.
because my goal is not only the
Exactly.
training data, my goal is generally all data
Mm.
of this sort. We want it to be generalizable.
Yes, so that's the key word. Like you would like this model to generalize to data that the model hasn't seen. So right now, we're really not doing things properly in the sense that usually you have something called the training data and the test data. The training data is the data that the model sees, the model trains on. But then when you go and see how well this model is doing, you use some data that the model has never seen before to see how it does. So in other words, you have to compute the loss using data that the model hasn't seen. And here we're just cheating. We're in the test loss that we computed here, we're just using the predictions from the network and comparing this to the same Y data that was fed into the training. This is the ground truth that we created from the beginning. Typically, you would like to compare these predictions to some test data that the model hasn't seen. So if the model is really, really just representing these training data really well, anytime you give it data that is slightly different from the training data, the model performance is going to be really bad. Okay, and this is, as you mentioned, this is called the overfitting of the model. All right, so I would like to now do something to shake your faith in the entire paradigm of neural network training, and I'm just going to rerun the entire code. And look at this loss here, it's 0.2. Let's rerun it again. Oh, so see now it looks actually different, looks better, and we got like a lower loss. Okay, so let's run it again. Slightly higher, but still decent. Let's run again. Oh, this now looks slightly different. See this elbow here, meaning that the model was really stuck a little bit here, and then something clicked and then started to learn again. So you see that there is really like we're running exactly the same code. Oh yeah, the data itself is random, so it's not the same data. But even if we if we just use the same data and we run this many times, you're still going to see differences because every time you train a new model, you initialize the weights into using random numbers. And again, I'm saying we initialize the models using random numbers, but in real world applications and when you're dealing with larger data sets, there are some tricks that people use to try and initialize the weights in a way that can cause the model to perform better. But we're not going to discuss them in this course. Okay, I would like to really have. Oh, this is what I would like you to see. See now, this example, we have a training loss that is almost 1.8. So like, even though it looks like this went down quite a bit because it started at 220 and then 1.8, the loss is really huge. And if you look at the predictions now, the model is just predicting the average of the data, and the predictions are really, really bad. So what happened here?
I guess I don't know. It trained for too long that the parameters maybe were screwed.
No,
Like
no, sorry. We're not really continuing the training. That every time I'm stop and restart, it's just training a new network. We're not like this is not. Sorry, this might be confusing because I mentioned the checkpoints and whatnot, but we're not really saving checkpoints. We're not really continuing training every time. It's just a new example with new data. We're
oh,
basically just rerunning this every time.
so it's just random. Maybe the first time our weights were initialized at a point that was easy for the model to descend to the minimum, but the
Okay.
next time it was initialized at another point where it was difficult. Another time it was more difficult, so it's random.
Okay, but we're not really like just getting bad performance. There's something here that like we're just getting a flat line. And like when you look at the correlation here, it's not defined, which tells us that the data has no variance. So meaning that if if the correlation is not defined, without getting too much into the math, it tells us the variance is zero. And then because we're trying to divide by zero, this is wrong. I think there's also like some um yeah, there's the same error as actually we can see here. So why did we run into this problem? How can we troubleshoot? Let's think about it this way. How can we troubleshoot? If I train the model and I end up with this, how do I troubleshoot? How do I know where my model is getting stuck?
I could print the loss at every step and see when does it go wrong.
Well, this is what you have here.
هو اصلا مش طبيعي ان هو يبقى اللوس اكتر من واحد ففي حاجة abnormal يعني حصلت لان المفروض اللوس بيتراوح ما بين 0 و1
I I would like to disagree with you, Noor.
اوكي
The loss here is just a function of the loss is just basically the MSE. So this is basically a numerical like if your X and Y data points are like massively in terms of like they are 500 and 200 and 300, the absolute value of the loss is going to change. There's nothing that says that the loss needs to be between 0 and 1. We're not really standardizing and normalizing anything.
اوكي
So something else has happened. So
I think, yeah, sorry, can I just say something about like, I think we missed like or we, there's two valleys, and then I think maybe that's the point that we missed the global minimum, and then we leaped to another valley, and then
okay, so these are all speculations, but we're trying to be scientists here, right? So how do we really understand what the model what went wrong with the model? What do we need to look at? Can you think about something that we can use that we can look at to try and understand what happened?
gradients
Do the gradients have any value, or do you mean the parameters? Like you're getting close.
يعني البارامترز اللي طالعة بعد ما عملت باك propagation عايزة
تمام.
اشوف ايه اللي طلع
Okay, so how do we visualize these parameters, or how do we check these parameters? Remember
كان
this
في اللي هي دوت
state.
ستيب دي اللي هي بتعمل ابديت.
There's an easier way. Remember this method here, state underscore dict, right? So if we basically just use our ANN reg and call the state dict, this should print every parameter we have, right? So we have one of the weights 0.3, one of the biases minus 0.7. The second weight is minus 0.74. And then the last bias is 0.0712. So do you see anything here that might be of a reason why we're getting what we're getting? Think about the flow of information. What we're doing in the network is we're passing the input, which is an X value, multiplying this by the weights, and then adding a bias term, which is a negative number, and then passing this to a ReLU. What does the ReLU do to the data?
ماكسيمم ما بين 0 واي حاجه اكبر. اوكي ده عشان كده هو نيجاتيف. اوكي ماشي.
So if the value is negative, because this bias term is a negative, the ReLU is going to output a 0, right? And then the 0 gets multiplied by the weight, the next weight, and we add a bias to it, right? Now, what would be the gradient if the output of the only hidden layer we have in this node is 0? What would be the gradient?
هتبقى الايرور هيبقى واحد.
The gradient would be 0. Every time you try to calculate the gradient, because it's 0, the gradient is going to be 0. Okay? And this is a problem we described when we discussed the ReLU called the dying nodes, right? Because in here, the linear output in cases like, because this bias is a negative term and looks like it's a bigger number, looks like when we feed something into it, it becomes a 0. And every time the ReLU is just inputting 0. And the model is calculating the gradient. And every time the gradient is 0. So it's really, really not learning anything. Like if you come here, this is really, really, it doesn't matter how many times it sees the data, the node is stuck at 0. And the node essentially died. That's why we call it a dying ReLU. It's not able to update the parameters because every time the gradient is 0, because then in the step parameter, you have the new parameter equals the old parameter minus the learning rate times the gradient. The gradient is 0. So every time you end up with the new parameter equals the old parameter. So the model doesn't really learn anything. It doesn't matter how long you keep this going, because you have the dying ReLU problem, the dying node, you're not going to learn anything. And that's why the prediction is basically just a flat line. The model hasn't really learned anything. It's just a random average of the data points. Does that make sense?
اوكي فهمت.
Okay. So how do we fix it?
احنا
I
لو
mean-
بدلناها مثلا بتنش اعتقد هتبقى
Or
أفضل.
leaky ReLU.
Leaky ReLU, right? So we can give it a variation of the ReLU function so that it actually just accepts a little bit of negativity in the network and it doesn't die. So like if I come here and I just ask it to use the leaky ReLU instead of the ReLU, and again, this is predefined in the torch module, then we can get away from that problem. So if I run it again, I go down here. It seems like we're basically back to where we were, and we can run this many times, and every time looks like we're a little bit more consistent. So look at this landscape. See, this is very different. This is really good. See, we started at like actually hit like a really good loss at like a very early epoch. When we look at the correlation, this is really, really good. And you see that this is not a fully straight line because we have this nonlinearity, but it's actually accommodating like these data points, and the function looks like this. So the correlation is pretty high. So I mean, this is the difference between using this versus like linear regression, for example, that the function doesn't have to be a linear function because we have this nonlinearity introduced by the value. But you can kind of see that now we've run it like a few times. Oh, now we've run into the same problem again, I guess. Oh, now we've run into the same problem. So what would be the reason why? Like we use leaky value. Why did we run into that problem now?
So after we use the leaky relu, we still have the same problem.
Yeah, looks like it. This is using the leaky value, and we still have the same problem.
Could this
Looks like
be because the value slope is not big enough?
yes, it could be that the value slope is not big enough. So we're still, I think if we zoom into this, the gradient is not exactly zero, but because of the learning rate we're using and the gradient being calculated is really, really close to zero, that we're not really observing much change. So in that case, even though we're using leaky value, I don't know what the default parameter is here, but sometimes I think it might be like 0.001 or something. So when we have a value that is still like 0.001, oh yeah, there we go. So if when we print this, it tells you here the negative slope is 0.001. Oh, sorry, 0.01. So like 1%. So it's still allowing for negative numbers, but that negative number is really tiny. That when you have a value close to zero, that your gradient is still very close to zero. So you're not really updating the weights by much. So you have two options here. You can either increase the negative slope or you can increase your learning rate. And I think the safer option for me personally would be to increase that slope. If you increase that slope a little bit, so maybe if we just pass in the negative slope equals maybe 0.1 instead of 0.01, maybe this would avoid the problem better. So like we can try this and see if we still run into the problem. So it looks like it's training well. Yeah, 0.15. So it's gotten down really well. 0.2, that's fine. 0.4, not the best. We've done better. 0.16, 0.2, 0.2, 0.2. So I mean, we could keep doing this for long, but it looks like we're getting some consistency here. We're not getting stuck the same way we were stuck before. Okay? Okay, I think this was a good exercise to understand like the practical implementations of this. And you can imagine that even though the implementing these things are really simple using PyTorch, if you really don't understand what's happening under the hood, you can't really troubleshoot. You can't really think about solutions. How do I know? Like this was a pretty simple problem, right? I mean, a pretty simple solution. We just change the activation function, change the parameters of how the leaky value is defined. You can play around with learning rate, and the good thing is there's a lot of theoretical basis to some of these choices that you can make, but you can also empirically play with things and see how they behave. And then one question that no one has asked here, like we've trained maybe like 20, 30 models here. How do you know which model to pick? Like which model do you push to production? Which model do you deploy for actual use? The answer is usually you train multiple models on multiple machines and you compare them, and the better model is basically what you pick. This is the easy way. Like I personally, when train models, I train models usually in triplets, like 3 models, because my training takes a long time. I can't really train like 10 models or anything. There's only so many GPUs I can use, so I usually train models in triplets, and I haven't seen a single time when I got like 3 models that perform the same. There's usually one off model that is like very weirdly like hasn't learned anything. And maybe two are doing competitively well, like one is slightly better than the other, something like this. Um, and again, there's probably some parameters that I can tweak. And this can get like very, very quick into like a deep rabbit hole that you can't get out of. Okay. We're running out of time, so I'm just gonna show you quickly an example of. Okay, let's just clear everything, run everything. I'm gonna show you. There was a one nice thing that I wanted to show you because it touches on another important concept, which is the normalization. So where do we go from here? Okay. And for the sake of time, I mean, you have this code, it's properly commented and everything, so you can go and read what I'm trying to tell you here. But I'm just gonna take this example here, which is instead of the y, like when I'm creating the data, instead of the y being defined as x plus a random number, I just added like a parameter m here at the beginning of the function, and I would like to just know that, or I would like to test how the training looks when I do when I try different values of m. So basically, I'm changing the relationship between x and y, and then I'm trying to see how this affects the model patterns, basically. And basically, just in the interest of time, this is what I wanted to show you. I'm plotting side by side two plots here. This plot is the actual m value in the y. Like this is not the model parameter or anything. This is the m that I just showed you in how the y is being calculated. And I mean, if you look at this plot, like on the left hand side without this, you would say, okay, the slope that is probably like maybe like 0.1 or something, this is the best slope, right? But then when you plot the correlation between the real data and the predicted data, this is the worst correlation. So how come this is the minimum, like how come this is the least loss? Like this is what I've been telling you for the last 4 sessions. We're trying to minimize the loss. And now I'm showing you a bunch of models, and the one with the lowest loss is doing really bad in terms of like correlation between predicted values of y and real values of y. Why is that the case?
Maybe it's not linear.
What is not linear?
So maybe it's not like, or not linear, not a regression that have a continuous values. So maybe you have
It, I,
to,
it doesn't matter here. Like what I'm seeing you is a very kind of conceptual thing. Like you basically have a grid, like a grid of different values, and the relationship between the loss versus these values, right? And what you're seeing here is the value that corresponds to this loss is the value that is doing really bad in the model performance. So it's either that I lied and we're not really trying to minimize the loss, there's something else we can do to improve the models, or there's something that we're not paying attention to. This has a little bit to do with something that Noor said. Can you think about it?
Is it that we don't want the slope to actually be at 0? Because this is
No,
when
we actually, at the minimum, the slope is actually supposed to be 0. Remember last time when we talked about the slopes and the increasing, the decreasing, at the minimum, the slope's actually supposed to be 0. Okay, I'm gonna spoil it for you. The difference is because we are multiplying, hold on, because we are multiplying y by m, when the m is really, really tiny, the y values themselves, the range of the y values are really tiny. So we're looking at the loss here, we're looking at the absolute output of the MSE function. So like we're comparing the MSE from one function to the next, but this really doesn't mean that if the absolute value of the loss from this function is higher than the other function, that the second function is doing better. Because what we're comparing are the absolute values of the loss themselves. So how do we get away from this? To get away from this, we can simply just standardize the y output. So like we take the prediction we take the real y here and we standardize this so that when we compare the predictions, along a standardized y value. So all we need to do here is, instead of calculating the loss, this code is going to look slightly different because I just wrapped everything into functions rather than running them separately, but you can look through it and see it. But basically what I can do here is, if I take the y and standardize it, let's say build a standardized value, which basically subtract the mean and divide by the standard deviation, and now I compute this, the losses with relation to the standardized values rather than the raw y values. I'm hoping that the kernel died. Anyways, I'm hoping that once we do this, it's gonna give us the proper format that we're expecting. Hold on, this is running. Still running.
باشمهندس هو ليه ما قلناش ان هي مثلا اوفر فيتنج، يعني loss زيرو بس الموديل performance at testing مثلا او زيرو؟
The loss is not exactly zero. The loss is slightly higher than zero, but because the y itself, like let's say the y value is 0.005 and the predicted value is 0.007. When you calculate the MSE between these two values, the absolute value of the loss is going to be less. So now you see how it looks when we just use the standardized y. This is kind of more of what we're expecting to see. Now at this tiny slope, the loss is actually the highest, which corresponds to the worst performance. See, now after we fixed the y, now that we standardized the y, when we were comparing like different values of y, we're not really concerned about the absolute value of the loss because we've standardized this between 0 and 1. Now when we're doing the MSE, now the comparison becomes more plausible between different models. Okay? Good?
Can you repeat the last part? Like why? How does standardization makes the comparison more more correct when we compare them all?
So when, like, think about it this way, instead of taking the absolute value of the MSE, you're taking this as like kind of like the change, or like what's the percentage of change between the loss here and the standardized value of y.
Okay.
Like you've taken, instead of having y that is the range of y between 0, let's say your y values range between 0.005 and 0.007. You've taken this and scaled this into values between 0 and 1. So the maximum value becomes 1, the minimum value becomes 0. And now with every model, you're comparing across that same scale of the standardized y's.
Okay.
You're basically scaling your values to be within the same scale. So it doesn't matter what the absolute value of your y is, you're putting it somewhere on the scale. And now you can truly evaluate how the prediction varies from the real data.
I get it. Nice.
Okay. And this is like, this was a segue to tell you that data normalization in some of these layers, we haven't talked about data normalization at all, but this was an example of how important data normalization is. And this is kind of similar to when you do, for example, like PCA. You always do scaling of the data before you do PCA. And the reason why you do this is because if you have one feature that goes from 1,000 to 10,000 and another feature that goes from 1 to 10, you cannot treat the variance between the features in the same space. You have to scale them down to be on the same scale so that you then can more objectively calculate the variance between them. And this is exactly the same problem we ran into here. Hopefully that makes sense. We didn't really get into the classification part of the data, but you have the code. You can run it on your own, and we can quickly talk about it next time before we actually discuss newer topics. Sorry, it took longer than expected to explain some of these things. I really wanted to go through the entire notebook, but يعني ملحوقة إن شاء الله. If no more questions, I'm gonna leave you إن شاء الله ونتقابل على خير الأسبوع الجاي.
Thank you very much. I really enjoyed this. Thank you.